So one thing that we talked about when we talked about isomers was looking at stereoisomers, where there was something different about the orientation of groups around a carbon atom. And we see the same thing happening in our carbohydrates. Now typically we were looking at much smaller molecules, but the same thing applies here for our carbohydrates. And what we can see is that just with our 6-carbon carbohydrates that are all aldehydes, we see that we actually have all these different options for how they are arranged. And the way that these differ from one another is because of the orientation of these OH groups and H groups relative to one another in each of the molecules. Now, in this drawing, it doesn't appear that there's actually any stereochemistry, any three-dimensional orientation. But for carbohydrates, because there are so many molecules, we have kind of come up with this shorthand way. And so this actually does show us something it's about stereochemistry. And we'll talk about that in just a minute. But it's atypical. So normally a skeletal structure doesn't necessarily show us anything about these orientations, but in this case it does. And so as we look through here, we see the same features on every single one of these molecules. We see we have an aldehyde group, and note how the aldehyde group is written here at the end. We have this a CHO, and what that is showing us is that we have a carbon with a hydrogen attached and double bonded to an oxygen. So similar to how we talked about our carboxylic acids, how we'd write this, but we really mean that we have this. The same thing is true for our aldehydes. We write it one way, but what we mean is this, just so we can kind of abbreviate the drawing a little bit. So each of these are, in fact, aldehyde groups on the end. Each of our other carbons has one OH group attached and one hydrogen, and then we have down here, we have a carbon with 2 hydrogens and one OH group. Now this is some of the stuff that we're going to be looking at in our groups this week. Now I'm talking about the stereochemistry and about these orientations as well. So we will be seeing this again. So let's go back to what we talked about in looking at stereochemistry before, when we talked about enantiomers and looking at chiral carbons. And so how many chiral carbons are in D-fructose? And so you're given the image here of D-fructose. You want to go through there and figure out how many chiral carbons are in that molecule. So take a minute to pause the video and look at each of those carbons and decide which ones are chiral and which ones are achiral, which means not chiral. Great. Hopefully you paused and did that. We're actually going to go through each of these carbons and decide whether they're chiral or not. Remember that for something to be chiral, it has to have 4 different groups attached to that particular carbon. I'm not looking at the whole molecule. I look at individual carbon atoms to decide whether that carbon atom is chiral. And if a molecule has at least one chiral carbon, then we describe the entire molecule as being chiral. But right now what I want to worry about is I want to look at each individual carbons. I want to know how many carbons are in fact chiral. So I look here at my carbon number 1. I see that it has 2 hydrogens attached to it. So immediately I know that it is not going to be, because I have 2 hydrogens, and in order for something to be chiral, it has to have 4 unique groups attached to it. For carbon number 2, I see that this is also not going to be chiral because it only has 3 groups attached. It has this group up here, so this whole group. It has a double bonded oxygen for its second group, and its third group is this whole rest of the molecule here, but I only have 3 bonds to that carbon, therefore it's not going to be chiral. Now I'm going to look at carbon number 3 here, and when I look at that, I've got to make sure I see that I've got an OH group, I have an H group, so I have 2 unique groups, and then I look up here, and this chain is going to be a 1 group, and the rest of this down here is my 4th group. So I do have, in fact, 4 different groups attached. Note that this carbon and this carbon is not what I have to worry about. I have to worry about the whole rest of the molecule. So I have 4 unique groups attached. So I see that carbon 3 is, in fact, chiral. So I'll put X's on these. When I look at carbon 4, similar to how I looked at carbon 3, I have 1 group, 2 groups, 3 groups. I can look at this whole big part of the molecule, and 4 groups. I'm looking at everything that's attached to that carbon. And so I have another chiral carbon. I look at number 5, carbon 5 here. Remember there's carbons there, we just don't show them in the middle. And so we have a hydrogen, an OH group, We have this whole big rest of the molecule, and we have this rest of the molecule. And so what we see is that this is also chiral. Now be careful, even if you have one that's in the center of the molecule, so we have 6 carbons here, so we don't have to worry about it. But if we have an odd number of carbons, note that even though there are the same number of carbons attached, where if I say we had 2 carbons in either group, we have to look at not just the carbon atoms, but everything that's attached to it. So these whole rest of these molecules we look at from the top of the molecule to the bottom are always going to be different from one another, because the top will always have an carbonyl group, either as a ketone or on carbon 1 as an aldehyde, and down here we don't, we just have our OH group. So we won't always have different groups on the top and the bottom. Now look at the carbon 6 here, and I see again that I have 2 hydrogens attached to that carbon, and so I have not chiral there, or achiral carbon. So in this molecule, I actually have 3 chiral carbons. And what this means is that every time I add an additional chiral carbon, I'm adding more options for the stereochemistry. We can see that there are more different ways to arrange these OH groups relative to one another. So when we look at this molecule, here we have glucose, we have our 6 carbons, we have our aldehyde group here at the end, we have all these OH groups. And what I see is that in this case I actually have 4 chiral carbons. So what we'll find is that the carbonyl carbon is never chiral because it only has 3 bonds to it. And that the carbon at the bottom is not chiral because it always has 2 H's. But all these kind of carbons in the middle are always going to be chiral. So we have 4 chiral carbons here. And every time I have one more chiral carbon, I increase the number of ways they can be related. For example, here in glucose, I have hydroxyl on the right, left, right, right. If I change just one of those, then I'm going to have a different molecule. It's going to have different properties, different characteristics, even though it has the same molecular formula, which is what makes it an isomer to begin with, and it has the same kind of connectivity, but the orientation is different around those carbon atoms for each of the OH and H groups. So even just flipping one of these, the OH group over here from the right over to the left, is going to make this actually a different molecule, a different isomer of that molecule. So the more chiral carbons I have, the more stereoisomers I can have for my structures. So what we want to look at, there's a couple things going on in this picture that we want to worry about. The first thing is I want to look at what we see as we go from top to bottom here. So I said that we can draw molecules using the wedges and dashes, and we've seen that to represent the 3D. The solid the solid wedges mean coming out towards us. The dashed lines mean going away from us. So we can show that geometry with those wedges and dashes. But when we're drawing carbohydrates, this can get very complicated very quickly because we have so many wedges and dashes and how everything is related. And so what we actually look at are what are called Fischer projections. And so what we do is we basically just kind of flatten the molecule when we draw it. And when we do, we know that if we see a Fischer projection of a carbohydrate, we know that it has 3D orientations, we know that it has a 3D geometry, and we know that it would have geometry comparable to this, but it's just been flattened out. And we'll see the same thing as we get into bigger and bigger molecules. We'll simply flatten those molecules out, and as long as we write it all the same way, then when we're comparing molecule to molecule, we can make comparisons of geometry even though the structure isn't specifically showing that three-dimensional geometry. So I flatten my molecule out here. What I see is my H is here on the right, the OH is on the left. My carbon up here, I have my double bond oxygen and my hydrogen, and at the bottom I have the CH2OH. And the reason I don't need to worry about the stereochemistry here is because I don't have any. Remember, this is an achiral carbon because it has those 2 hydrogens, so there's no stereochemistry related to this carbon or to this carbon. The only ones that really contribute to producing more stereoisomers are in fact these chiral carbons in the sequence. So we can do that whether we're talking about this version of glyceraldehyde or our version over here. Note, and we'll talk about the difference between these two structures in just a minute. Again, we've just flattened the molecule and we show our OH group on the right, our H group on the left here, our CHO and the CH2OH have no stereochemistry or no mirror images for them because we have 2 groups attached to the carbon here and we only have 3 groups. So not chiral, therefore they're not contributing to the stereochemistry of the molecule. So we flatten these out. So when we're looking at these two, because we are looking at mirror images, because there's stereochemistry, because there's an orientation of them, what we have here are non-superimposable mirror images. Therefore, these would be enantiomers. These are non-superimposable mirror images. Now notice in these molecules we have one chiral carbon, one chiral carbon. When we go beyond having one chiral carbon, we don't continue to use the term, or just use the term enantiomers. We have a couple of other words that we're going to throw in there so we understand the way they're laid out. Now notice when we take the mirror images of these molecules, we don't actually take any kind of a change in these groups here at the bottom and the top, because remember, those are not actually giving us anything about the stereochemistry of the molecule. We want to show those exactly the same way. So for these, and remember, if we look about these as being in the plane of the mirror, they're not actually going to reflect. We're not going to see that change. So whenever we're doing mirror images with our carbohydrates, so if we're looking at this, we can see these are mirror images of one another. Only worry about reflecting about across that kind of chiral carbon. So leave everything else drawn exactly the same way. And the reason we do this is because we want to make sure that we're actually drawing two different molecules and not drawing the same molecule in two different ways. So again, only worry about the orientation with respect to that chiral carbon. So just basically the H and the OH groups get flipped. And sometimes that's not as easy to see when we're looking at our Fisher projections, because we're not showing the three-dimensional structural features. However, they are there. So just leave these as is when you're looking at these mirror images. Only flip the H and the OH to make sure we're actually drawing the other isomer and not just a different drawing of the same isomer. So looking at our 3D structure, we can look here at this kind of wedge and dash projection. They're showing dashed lines here like we were showing the lined or the dashed wedges before. And so when we take this molecule and I want to put it into something that looks like a Fisher projection, and again, this is just something that's done for carbohydrates because the molecular structure gets a little bit more complicated with so many of these atoms involved, that we basically take it and flatten it so we end up something that looks like this. It's still representing the stereochemistry. This is not just a skeletal structure. Even though I know it looks like a skeletal structure, it is in fact a Fisher projection. The way it is drawn gives information about the 3D orientation of the molecule, and we're using these for carbohydrates. This is used for other molecules as well. Our primary concern with it will be as a carbohydrate. We still see our chiral carbons, and we still see that our OH is on the right, left, right, 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 left, right, right. Nothing changes about that. The last thing we're going to look at here, and we'll explore this more in the groups this week, is this idea of L-glyceraldehyde and D-glyceraldehyde. You may have seen these notations earlier when we were looking at the mirror images. And what we see is this is just a way to represent something, and it tells us something about which version of the molecule we're going to look at, because if I take this molecule, these are in fact mirror images of one another, and so we use this prefix of an L or a D to indicate which one we're talking about. And in nature, we actually only see the D sugars or the D saccharides or D carbohydrates. Remember, they all mean the same thing. That D stands for dextrorotary, and then the L stands for levorotatory. And so what we're worried about here is where is the OH group on the last chiral carbon in the molecule. Now for this molecule, glyceraldehyde, there's actually only one chiral carbon right here in the middle, and so I only have to worry about that one. If we had many, many carbons, I would only worry about the last one, the one closest to the bottom, the one farthest from the aldehyde or ketone group. In this case, that's all this one carbon because there's only one, but I'm going to go to the very bottom, get to the last chiral carbon, and see where is the OH group and where is the H group. If the OH is on the left, I'm going to refer to that as the L-glyceraldehyde. If the OH group is on the right, it's going to be the D-glyceraldehyde. And these two are, in fact, mirror images of one another. These are enantiomers. And if we had multiple carbons, we can actually draw the enantiomers of those, but there are also other ways that those molecules, those OH groups, can be arranged with respect to one another. And when we get into the group activity, we'll see the words diastereomer and the word epimer. And so similar to enantiomers, it tells there's some relation between two molecules. In this case, for enantiomers, they are non-superimposable mirror images. And diastereomer, epimer will have similar definitions that have to deal with the stereoisomers as well. So we'll pick up with this in the groups on Tuesday and Wednesday. If you have questions, please feel free to post them on Piazza or ask me tomorrow or Wednesday in class.